Problem statement. Can you tell which of the following data has more spread? Is it A, is it B, or is it C? This session is about answering these types of questions. This session is about variance and standard deviation. By the way, the answer is A. So variance is a measure of how much dispersed or spread or scattered your data is from its mean value. So let's say you have a data set with values x1, x2, all the way to xn, and you know its mean value. So the formula for variance is given by this expression. Now, one thing about variance is this: it is difficult to interpret, it's difficult to understand because of the squared unit, because of the presence of this 2. And what happens is this: if x1, x2, xn, let's say they're given to you in kilogram, then your variance is going to be in kilogram square. And this square can be a little bit hard to understand. And this is where you get standard deviation. This actually helps you out. So in standard deviation, you take the square root of variance. Now, this way, your standard deviation, it becomes easy to understand, easy to interpret because it is in the same unit as your data points. So for example, if your x1, xn all the way are in kilograms, then your standard deviation is also going to be in kilogram. In this particular picture, you can see this data has smaller variance. Most of my data is between this range and this range. Over here, you can see this data right here has a high variance. You can see it's spread between here to here. So in this case, your spread is only here. Over here, your spread is a little bit higher. So let's start with an example. Suppose the monthly income of a population in a city is given by these numbers right here. Calculate the variance and standard deviation for this population. So in this case, my size equal to 10. In this case, my average value, my main value is going to be the sum of all the numbers and you divide by 10. That's my size and my answer comes out to be 5. So my mu in this case is 5. So this is my formula for variance, okay? And I expand this expression and this is my expanded expression right here. Substitute my x1 and substitute my mu. Substitute my x2, substitute your mu, and this will give you the answer. So your x1 is 1, right? This is your 1 right here. You can see 1 minus mu, and then square the term, and you come with this expression right here. Same thing with the next expression. You have x2 right here. So x2 minus mu square, and this is how you get this second expression. Same thing with the third one. You have x3, which is 0. So x3 minus mu square, and you can keep going like this. So this is how you get this expression. Okay, solve this expression, and the answer comes out to be 16.8. So this one, let's say if your unit in this case is monthly income, it could be dollar. So this is going to be dollar square. If it is rupees, it's going to be rupees square. So whatever currency you're using is going to be square of that currency. So the standard deviation in this case is going to be under root of that number, and the answer is 4.1 dollar if you're using dollar, or rupees if you're using rupees, or some other unit. You can see that by looking at this number, you can tell that there is some spread, there is some dispersion in the data. You can also see that by looking at the numbers right here. So you can see, let's say 110, you see you have 1 right here, you have 1 right here, you have 0 over here, you have another 1, you have another 0. You can actually count over here. Okay, this is actually, I'm just plotting these points on the number line, and I have 2 5s right here. Okay, then there are 2 9s. Okay, you can see that there is a 9 and there is a 9. Then there is a 2 10s over here. Okay, so there is a 10 over here, 10 over here. So basically, you can tell just by looking at this right here that there is spread in your data. This is your average value, your mu is average, and your data is basically spread around your mu somewhat. Now let's consider this example. Consider the package weight in kilogram produced on a production line. So these are my numbers. These are the weights of the packages. Calculate the variance and the standard deviation for this population. So in this case, my size equal to 10, same size as the before, and my average value, the main value, is going to be the sum of all the numbers divided by 10, and the answer comes out to be 4.8. This is my mu. So use your variance formula, expand, and then substitute your values. I substitute my values. So x1, right, 4. x1 minus mu square is this expression right here. Okay, x1 is 4 minus 4.8 square. Then x2 minus mu, your x2 is 3, right? You can see is 3 right there. So 3 minus 4.8 square. Then you have x3, which is 5, 5 minus 4.8 whole square, and you can keep going like that. At the end, your answer would be 1.56. So in this case, it's going to be 1.56 kilogram square. Calculate your standard deviation, and the answer is 1.3 kilogram. And you can see in this case, the data is less dispersed. If you plot these numbers, if you plot this data right here on your number line, it's going to look something like this. You have two threes, okay, you have two fours, okay, you have three fives, all right, and then you have two sixes, and then you have one seven. You can actually count over here, and you can see that your data is kind of like spread around this your mean value, and it's not very much dispersed a lot. It is dispersed but not a lot. Now, let's take a look at this third example. Consider the time interval in seconds between operations on an assembly line for all 10 machines. So these are your data right here. These are your time in seconds. Everything is 5555. Calculate the variance and standard deviation for this population. Here, my size is equal to 10. Calculate your average, add all the numbers together, divide by 10, and the answer is 5. This is my mu. Use your expression, expand the expression, substitute the value, okay, 5 minus 5 square, 5 minus 5 square, 5 minus 5 square, all the way up to 5 minus 5 square, and the answer is 0. So your variance is 0, in this case 0 second square. How about your standard deviation? Well, square root of this would be 0 second. So the data has no dispersion, and if I plot this on a number line, you can see this is my average value right here, 5, and look at all my data points. It's all exactly at 555. So there is absolutely no dispersion over here. Now the conclusion. So if your data points are far from the mean or far from your average value, your variance is going to be large. In other words, your data is going to be more dispersed or more spread. If your data points are close to the mean, the variance is small. Your data is less dispersed or less spread. And as you can see by looking at this case A, okay, here in your case A, you can see your data are very far from the mean. You see, this is my mean right here, and look at this. Some data is over there, some is over there, and there are two over here. So there is a more spread over here, and that's why your variance came out to be 16.8. And look at the second example right here. In this case, my data has some spread. My average was 4.8, right? And you can see there is some spread, but not as much spread as this one. This one has more spread. This one has less spread. And then look at this case C. Everything is 5555. And you can see there is absolutely no spread over here. In this case, my variance is 0. So let's try to understand how a standard deviation controls the spread of your distribution curve. So I have this 1050 data points, okay, and basically what I did, I'm just copied and pasted 100 data points, right? These are 100 data points from the 1050 data points. And in this case, my sample mean was 5, okay, and the standard deviation in this case was 4. And I plotted this, and this is my histogram right here, and this is also plotted a distribution curve right here, and you can see the distribution curve actually has some spread. So this is how your distribution curve looks like. Your standard deviation is 4. Now I'm basically taking same number of data points, 1050 data points, and I copied and pasted 100 sample 100 points over here. My mean in this case was 5, exactly same mean as the one over here. So they both have the same mean, and my standard deviation in this case is 1. So you can see how your histogram looks like, your curve looks like right here, okay? So just by looking at the curve, you can tell that if your standard deviation is high, your spread is going to be a little bit more wider. And if your standard deviation is low, your spread is going to be low, like this over here. So why do we need to measure variance and standard deviation when you can actually find the spreadness using your variance, or you can use your standard deviation? Well, the answer is this. Your variance is the average squared deviation. You can see by looking at the formula right here. Okay, it's the average squared deviation from the mean value. So if your data, let's say, is in centimeter, then your variance is going to be expressed in centimeter square. And centimeter square, like squared units, they are not directly interpretable. You cannot really understand that. Nobody says the spread of your height is 100 centimeters square. It doesn't make sense. But by taking the square root as in standard deviation, like this right here, okay, I'm taking this square root right there, you bring the units back to your original scale. So if your data is in centimeter, then your standard deviation will bring it back to centimeter. So if the mean height, let's say, is 170 centimeter, and let's say you do the calculation and your variance comes out to be 100 centimeter, then your standard deviation would be 10 centimeter. In other words, now you can say that most data is within 10 centimeter above and below the mean. If this is your 170 centimeter, this is the average, this is the mean. That means 10 in this direction and 10 in this direction. That means most data is between 160 and 180 centimeter. So now let's try to understand the difference between population variance and sample variance. So in your population variance, let's say your population is of size n, and this is my data point right here. So the population variance is given by this formula right here, okay? On the other hand, your sample variance, let's say you draw a sample of size small n. So let's say this is your population, okay? This is my population, and from this population, I draw a small subset of sample. And the size of this small subset of sample is small n right here. So the formula in this case would be given by this. So the difference between this and this is that you're dividing by capital N over here, and in this case, you're going to divide by n minus 1. That's the only difference. And of course, you use a different notation. So you use sigma square to denote your population variance, and you use S square to denote your sample variance. Uh, So let's say how to decide which variance to use, population or sample. Well, if you're analyzing all the data from the group, then use population. If you're analyzing a subset, okay, let's say this is a subset, and if you're analyzing just a subset of your sample of the full group, then use your sample. So let's say, let's understand through some of this situation. Let's say you recorded heights of all students in a school. So since you record the heights of all students, in this case, you're going to use population. So you're going to be dividing by n in this case. How about if you took a random sample of 10 students? So I took a random sample, okay, of 10 students right here. In this case, since you're working with a sample, you're going to be dividing by n minus 1. Well, how about if you analyze every product made in one day? Okay, so this in this case, you're analyzing every product, that means your whole population right here. So you're going to be working with the population, you're going to divide by n. How about if you tested 20 random products to estimate the quality of a product? In this case, you're going to use sample because you're using a small subset of that.